Hi, today we're going to look at the third subtopic for DCC, the direct current circuit. The third subtopic is our Kirchhoff laws. Okay, Kirchhoff laws. Well, Kirchhoff law, we have two laws. The first one is the Kirchhoff first law. Okay, or you can call it also Kirchhoff current law, because it's related to current. Alright, so Kirchhoff first law states that the total current that enter a junction, okay, must equal to the total current that leave the junction. Okay, so that's a statement for the Kirchhoff first law. Now, when you say total, normally mathematically we use this symbol. The total current enter into a junction must equal to the total current that flow out from the junction. It must be the same junction, referring to the same junction. So this is the statement, and this is the equation. Alright, so Kirchhoff first law is actually very simple. So for example, okay, let's say you have a junction. Junction means you have a conductor connected to another conductor. So the simplest junction will be a T junction. Okay, a T junction. So let's say the junction is here. So we name it junction A. So there are possible three current, okay, like this and like that. So we call this one I1, this is I2, and this is I3. So common sense told us that if you sum up these two, it must equal to the third one. But some genius actually summed it up under Kirchhoff first law. So we have this using Kirchhoff first law. Okay, by an exam you cannot use this symbol to write the full thing. So Kirchhoff first law says that, okay, at junction A, the total current enter must equal to the total current leave the junction. So the total current enter the junction is I1 plus I2. So we have I1 plus I2 must equal to the total junction that total current that leave the same junction. Okay, so I3. So you have one equation. Okay, but normally in Kirchhoff law equation, it involves three currents, which you need three equations. So this is just one of the equation only. Alright. So other type of junction can be like what we call that, a cross junction. Okay, a cross junction. So this is a junction. So in this case, you might have four, okay, current. Okay, four current. So it can be like I1, I2, I3, and I4. So these two sum up must equal to the other two. So that is the cross junction. So the shape doesn't mean it must be in the shape of the cross. It can be any shape actually. Okay, it can be something like this. Okay, in and then out. Okay, and then out. So as long as the conductor are touching each other, where current is flowing through each other, it's called a junction. So in this case, it can be the same thing like this, in, okay, current, I1, I2, and these two are out, I3 and I4. Alright, so that is our Kirchhoff first law. Okay, so next we're going to go to the Kirchhoff second law, which is slightly more difficult. Okay, so our Kirchhoff second law. Okay, so B, Kirchhoff second law or Kirchhoff voltage law states that, we start with the statement first, states that the total change in potential across all the component in a closed circuit must equal to 0. Okay, must equal to 0. So mathematically, the total change in potential must equal to 0. Alright, so that one is a mathematical statement about Kirchhoff's second law. So the physical understanding of this thing is, let's start with a simple diagram. Okay, a closed circuit that consists of 2 batteries and also 2 resistors. So let's start with this. Okay, we have 2 batteries. Okay, they are all in series with 2 external resistors like that. So I call this one R1, this is R2, this one is epsilon 1, this is epsilon 2, which is the actually EMF. Okay, now when you talk about potential, a change in potential across all the components, these are components 1, 2, 3, 4, we got 4 components, and since they are all connected, it is in a closed loop. Okay, all components in the closed loop, if you measure their voltage, okay, and you sum that up, it equal to 0. Okay, but the question is, how are we going to measure the voltage change? So we measure the voltage change. Let's say this is our voltmeter. Okay, so at the voltmeter, your voltmeter, you have 2 electrodes, the red one and the black one. This one is a positive, this one is the negative terminal. So when you measure, okay, you measure the voltage across each of the component, the way you measure must be consistent. Let's say we start with this one. Okay, our first resistor. You look at the diagram, the red terminal is, if you are standing inside there, if you look outside to the measurement, your positive terminal is here, the negative terminal is there. So we have this okay, so this is the positive terminal, another one is the negative terminal here. Okay, and let's say our reading is V1. Okay, and then you go through another component, but when you go to measure another component, you move your voltmeter like this. So when you see, when you are standing inside, look at the measurement, the positive is still on the right hand side of the component from your point of view. So now you have, this one is the negative, another one is the positive. So now this is your value V2. Okay, value V2. And then followed by the next one, you go like this, then standing from inside, your positive os is on the right hand side again. So now we have our third reading. This is our V3, and this is a positive terminal. Okay, and then until the last one, okay, you see you go around like this, and now your positive, you're standing from inside, your positive is still in the same position. This is our V4. Okay, that is a V4. So if these are all their actual reading, then according to the Kirchhoff's second laws, okay, it says that the total change in potential must equal to 0. So when you sum up all these values, they're supposed to become 0. Equal to 0. That is a physical meaning of Kirchhoff's second law. Alright? So the measurement, when you are doing like this, there are 2 ways in looking at the way you measure. You're standing inside or you're standing behind the component. Okay, so if standing inside, your positive electrode will be on your right hand side, and then if you're standing from outside, go around the circuit, your positive terminal will be on the left hand side. So it's, everything is relative, but every component you do the same thing. When the positive electron is on the left, it's all the time on the left hand side. Alright, so that is the consistency in the measurement under Kirchhoff's second law. Alright, so the next one is, we're going to look at one example, okay, on how to use Kirchhoff's law to solve problem that cannot be solved using simple Ohm's law. Okay, So that will be our first example. Oh yeah, before I forgot, there is something else after the Kirchhoff's second law. We have this Kirchhoff sub-rules. Okay, Kirchhoff sub-rules or Kirchhoff convention that we have to follow. There are altogether 4 sub-rules. This is an EMF. This is a resistor. Okay. Current flow in this direction. In this case, current flow is in the opposite direction. They are actually opposite. First thing before we can analyze Kirchhoff sub-rule is we always want to know the potential change. Okay, when we go across a component. These are the components. Okay, so we want to go across a component from A to B, all moving from A to B, A to B, A to B. All right. So to make things easier, you just assume you are a positive charge. Okay, you are a positive charge which move from A to B with a certain velocity. Okay, so positive charge moving from A to B, positive charge moving from A to B, positive charge moving from A to B. Now, in this case, the first case, case A, where you are actually coming across a battery or a cell, you hit the positive terminal. Okay, so according to Coulomb's law, when you are, if you are positive charge and you come to a positive terminal of any kind of battery, you are actually losing energy because you do work against the positive terminal because you experience repulsive force. So after you cross the battery, your change in potential, which is VB minus VA, is going to become negative epsilon. You lost. Okay? You lost. But the other way around, if you are positive charge, you come across, okay, a negative terminal of a battery, you get attracted. Okay, you gain energy. When you gain energy, okay, this is what happened. You have positive epsilon. Okay, you have positive. So that is the first one, and this is the second one. Okay, so remember, when you come across, you analyze a circuit from a point to a point. When you encounter positive terminal, you lost that how much of potential. When you are moving from A to B but come across a negative terminal first, then you have gain in potential. By how much? The same amount as the battery itself. Okay, and then the next one is C. You look at how I label the current I. Current flowing from A to B. Okay, from A to B means potential at A is higher than B. Okay, potential at A is higher than B. In this case, it is the opposite because current flowing from B to A. So you have VA smaller than VB. Now, when you have a positive charge moving from high potential to low potential, your changes in potential, okay, is equal to VB minus VA. But your VA is larger than VB, so when you minus, you're going to get a negative value, okay, negative V. Well, that voltage across AB, okay, is the change in potential across the R. So that one is equivalent to, according to Ohm's law, negative IR. Alright? So that is our third sub-rule. And then the fourth one is delta B is equal to VB minus VA also. But current is flowing from B to A. That means B is higher potential. So now you're using a higher potential minus, you get a positive value. Okay, according to Ohm's law, that will be positive IR. Well, You have to memorize these 4 sub-rules in order to use Kirchhoff's second law. Okay, so that's why I say Kirchhoff's second law is much more complicated than the Kirchhoff first law. Okay, so now we'll look at one simple example. Okay, for Kirchhoff law. Okay, example 1. Okay, example 1. So example 1, I only give closed circuit with no